Hey, can you all hear me?
Yes.
Okay, great. All right, so we'll wait, a couple more minutes. Well, in the meantime, just copy this down right here. This is the next little thing that we're going to continue with section 2.3. All right, so let's get started. So yeah, we're continuing 2.3, which is the limit laws. In last class, we had briefly gone over, these laws. Now, these laws are kind of like quick tricks, I guess, or a faster way of evaluating a limit. Because if you recall from 2.2, how did we have to find the limit of a function? Well, we had to choose values slightly smaller than it, right? And then values slightly larger than that x value we were trying to analyze. Because remember, a limit's about the journey, right? Of basically, if you're approaching some number, where would your y value eventually wind up, right? And in order for that limit to exist, basically we had to be approaching that same y value from both the left side of that x value and the right side of that x value. If they both approach the same y value coming from both directions, then we said, hey, the limit exists, right? But if we got two different values, then we said the limit does not exist. So now with this right here in 2.3, this is thankfully the faster way. We don't have to do t-table stuff and figure out these values right here. But this is another little important concept right here. It says if f is a polynomial or a rational function and a is in the domain of f, then the limit as x approaches a of f of x is simply f of a. So what does that mean, right? Well, if we take a look at a problem, like here we have the limit as x approaches negative 2 of 2x cubed minus 4x squared plus 3x minus 9. This is a polynomial, right? Rationals are basically like fractions, right? Polynomials on top of each other. Now, if we were to plug negative 2 into here, would that be in the domain of f? And yes, it would be. So what do I mean by, oh, it's in the domain of f? Basically, if you can plug this number into your either polynomial or rational function and you don't have any discontinuities or zeros forming in the bottom, then you're good to go. And you just literally substitute the number in and work it out, simplified, and you're done. And in this case, we don't have any issues, right? Like if I plug negative 2 into here, we're not going to get zero in the denominator. That's impossible, right? Because the denominator in this case is 1. So if it's something nice like this, you just plug the number in. Oops. But as you're doing this, right, watch the arithmetic, watch the signs, the exponents, order of operations, all that good stuff. Like this is 2 times negative 8, right? And then this is positive 4 times a negative 4 is negative 16. And then minus 6 minus 9. So then we have negative 16 minus 16. I can combine these two. Why not, right? We get negative 15. This is negative 32 minus 15. And we finally wind up with negative 47 right there. So in this case, your final answer is negative 47. That would be the limit as x approaches negative 2 of this particular function. And again, as long as you don't have any kind of errors or something that's causing your function or rational function to be undefined, you can simply throw the number in. Now, this is the easiest one, right? Because life's not going to be that easy for the rest of the problems. There most likely will always be some kind of issue that we have to take care of. So let's see how do we do that, right? Like, what can we do right there? Or what do we do? So now we're dealing with a rational function, and usually these have some kind of issue when you're examining limits. Why? Because there's the potential for the denominator to go to zero. Remember, anything divided by zero is error, undefined, game over for that problem. So that does happen right here, right? Because if I were to throw in negative 2, you would see that we would wind up with 0 in the denominator. This is undefined. That's what we don't want, right? That's bad. So what we can do or try to do is manipulate our expression. Okay, manipulate meaning factor, multiply by conjugate, all kinds of tricks, right? Try to do something to get rid of that issue from the denominator or remove part of the denominator that's making it 0, right? Because if we can get rid of that, then we can actually figure out, hey, what is the limit? Now, for these types of problems, there's all kinds of things you can try, right? Like there's factoring, multiplying by the conjugate, the complex conjugate. If you have a trig function using trig identities, there's no hard, fast way of, oh, it will always work if I do it this way. And a lot of people get into the trap of, well, it's always got to be done by factoring or something like that. Like, no, in this case, it does work. In other cases, factoring is not going to work. So it just depends, okay? You can kind of think of it as like a game. So in this case right here, we definitely can factor the numerator. Like if you have no idea where to start, just ask yourself, can I factor something, right? Or pull out a GCF, something, right? This becomes x minus 4 times x plus 2 over x plus 2, right? And now if you notice, well, that's great. Why? Because we can cancel out that x plus 2 from the denominator. So all of a sudden, we have no more denominator. We just have a numerator. We have this expression left over, just x minus 4. Now, is it okay for us to plug that negative 2 into this expression? It sure is, because that's not going to give us a 0 in the denominator. So now we could say, oh, well, this is just negative 2 minus 4, and we get negative 6. So that's your answer right there. That's the limit as x goes to negative 2 of this function. Now, if you didn't do it this way and we did the t-table method, choosing values slightly smaller than negative 2 and values slightly bigger than negative 2, and we plugged them into here, you would see that their y values would be getting really close to negative 6 from both sides. But obviously, this was way faster, right? So again, factoring was one way to get rid of the restriction, right? Sometimes factoring may not be a viable solution. It just depends again on what your particular function is. All right, let's check this one out. The limit as x approaches 0 of this rational expression. Again, you can initially try to say, hey, let me throw this number in and see if I get something undefined. If you can throw this number in and get something that exists, right, like just a finite number, then there is no real work, right? You don't have to sit there to try to manipulate it. But right here, again, what happens when we plug 0 in? you instantly see that you have 0 in the denominator. 0 up top is okay, but the instant y'all have 0 on the bottom, you got to sit there and manipulate the equation. So what do? Right? Well, this kind of already looks kind of factored. Maybe we should break it apart, right? So, and see what happens. Sometimes when you're trying these things, like if you factor something and nothing cancels, or you break apart something and things aren't canceling, then just it doesn't mean you're wrong. It just means you need to try something different. Okay, and as you practice more of these problems, you'll sort of develop like an intuition about what should I do to simplify this. So let's just try to go out there and we can FOIL this out, right? That's what we'll do. FOIL. Remember, this is actually x plus 3 times x plus 3, right? FOIL is, this is not x squared plus 9. No. Remember, FOIL means first, out, first two, then outer, then inner, then last two, like that. So if I FOIL it, we actually get x squared plus 6x plus 9 ultimately. And then we still have that minus 9 that's left over, right? Got to carry that over. Don't forget that. But the red stuff is the FOIL of this x plus 3 squared. And we have x still in the denominator. So, I mean, maybe it looks worse to you, right? Because there's like, oh, there's more garbage up top. But if you notice, we can start to do things, right? Look at what happens. We can knock out the 9s. Well, that's nice. And now we're left with a limit as x approaches 0 of x squared plus 6x plus x, or over x. Well, there is more canceling that can happen, right? Because notice, look, this x and this numerator, they all share something in common. So I know a lot of people like to slash stuff out. They get slash excited, they start whatever crossing stuff out when you have fractions. But remember, in order to cancel things out from rational expressions, everything must share at least one thing in common. So right here, we can cancel out an x, correct? Because everything, there's 3 terms, 1, 2, 3, they all share something in common. It is x. So yeah, I can slash out an x. Be very careful, because let's say on the bottom you have like x minus 2, for example. You would not be able to cancel these x's out. Why? Because does the 2 have some kind of x multiplied into it or with it? No. So if you had some problem that was x squared plus 6x over x minus 2, and it said simplified, that's as far as it goes. You cannot cross this x out with these, because again, there's no x right here. But if this was like 2x cubed, for example, we could definitely reduce all these by a factor of x, right? Because they all share an x in common. So remember that. So yeah, we can cancel an x component out because they all have that. And in doing so, what are we left with? Just x plus 6, right? Remember, you got to divide this x into both quantities right here. X goes into x squared, x times. X goes into 6x, 6 times, right? And these knock out like that. But now, the best part is that we can plug the 0 in, right? Because we're not going to have any kind of undefined expression that comes from that when we do it. So this is 0 plus 6. And then we get 6 right there. So that's the limit as x goes to 0 of f of x, which is equal to 6 in this instance right here. So in this case, we didn't actually factor, right? We had to FOIL stuff out. So again, it's all about experimentation, okay? The goal is to ultimately get rid of that restriction or that issue. If you're working stuff out and it's looking more and more messy and things aren't canceling right here, then go back a couple steps. Try some other algebraic trick, or try some other trick. So now with this one, we have a root, right? Looks a little more nasty. We have square root of x plus 25 minus 5 over x. Be very careful. You cannot, and I know people want to do it. I know some people are thinking, oh yeah, x plus 25 under the root, that's equal to x plus 5. No, you cannot do that, right? I know some people want to do that. Lots of people like to do that. Remember, the square root of a plus or minus b does not equal the square root of a plus or minus the square root of b. You cannot separate stuff under a root like that if it's connected by multiplication, by addition or subtraction. The only way you can split stuff under root is if it's multiplication or division. Like if you had this, yes, it's fine to say, oh, it's the square root of a times the square root of b. Or if you had something like this, division, then yes, you can split it. These are okay. This is not okay. But a lot of people like to do that. No, I know it looks very enticing because 25 is a perfect square and it'll come out and knock the 5 out, right? And make things easier. But you can't do that in this case. So what can we do, right? You can't factor that. It looks pretty nasty. But when y'all have roots, remember, and you need to get rid of the root, and it doesn't matter if it's in the numerator or the denominator, what you can do is multiply by the conjugate, right? So remember, the conjugate in this case is it's the same terms up top, but you change the sign of the number in between only. So we're going to multiply top and bottom by the square root of x plus 25 plus 5. So again, the conjugate is whatever these two terms are, you keep them the same, but you just flip the sign of these two right here. If initially this was minus plus 5, this would have been minus 5 right here, okay? You don't change anything else. And why is this legal? Well, what is root x plus 25 plus 5 divided by itself? It's 1, right? So all this is, and 1 times whatever is just whatever it is, or the initial expression. So all we're doing is we're multiplying by a fancy form of 1. That's all. So why are we doing that? Let's see what happens, right? So up top, we have 2 terms times 2 terms. So we're going to have to FOIL, right? Got to do the FOIL again. So your first term is the root stuff, and then we have the outer, and then the inner. Oops. You have your inner stuff, and then you also have your last 2, like that. So if you FOIL, remember the first is root x plus 25 times root x plus 25. If you FOIL like roots together, what happens? The roots disappear, right? It's kind of like saying, what's the square root of 2 times the square root of 2? It's the square root of 4, which is just 2, right? But did we have to really multiply that out? I mean, you could have, but you could just understand, oh, these two are the same, so the roots get knocked out. Same thing's going to happen right here. So you're going to have x plus 25. That's your f term right there because the roots just get knocked out. Now we have to do the outer, which is root x plus 25 times a positive 5. That just becomes plus 5 root x plus 25. Now we have to do the inner. Negative 5 times this root. Well, it's just negative 5 times that root. And then we do the last 2, which is negative 5 times positive 5. That's minus 25. And then we have our denominator, right? Now with the denominator, if we multiply it through, is anything really going to happen? No, you have x times this root. You cannot multiply this x into the inside of this. Why? Because this is not in a root. So I'm just going to leave this in factored form. Yes, you could say x times 5 is 5x, but again, that's not gonna help in this case. It's not gonna make things any easier. So this looks pretty bad at this point, right? Because there's a lot of terms up top. But notice what's happening up top. We can cancel all kinds of things, right? Look, you can knock this root out. You got plus 5 of that root, minus 5 of that root, that goes. What else goes? Oh, the 25s, look, 25 and 25 go. So now, what are we left with? Well, now we have the limit as x approaches 0, 0 of just x over x times the root of x plus 25 plus 5. How about that? So if we plug 0 in, we still have 0 on the bottom. We actually have like 0 over 0 times something, and that's still undefined. But we can cancel, right? We can simplify this right here. Why is it okay for me to knock out these x's right here? Because this x is connected to all this stuff by multiplication right there. So that's okay. Now, important, when you cancel that x out up top, don't say there's nothing left up top. A lot of people go, it's nothing. No, because what is nothing? Nothing is 0. It's not 0 that's left up top. There's a 1, right? X divided by x gives you 1. Something else that people accidentally, or I don't know if it's accidentally, what they do that's incorrect is they'll move this thing up top because this canceled up top. No, you can't just say, oh, I'm going to move that up top. No, that's not mathematically legal. That stays on the bottom. So we have 1 over the root of x plus 25 plus 5. Now, if we plug 0 in, are we going to have any kind of weird restriction or error that comes up, or like a 0 that pops up in the denominator? No. So remember when we first had our problem, we just had plain old x in the denominator, and that was the issue. But now we've been able to algebraically manipulate it so that we're not just left with 0 in the denominator. And because that's the case, we can successfully or finally evaluate this thing. All right. So now we have 1 over square root of 0 plus 25 plus 5. If we work this out, we get 1 over square root of 25, right? Plus 5. Well, this is nice because it's a finite number, right? This is 1 over 5 plus 5. And then you wind up with 1/10 in that case. Even if this root wasn't a perfect square, right? Like what if it was square root of, say, 11 plus 5? Then your answer is just 1 over the square root of 11 plus 5, right? You would want to leave it in an exact form unless the directions specifically say convert to decimal, which they won't. They'll want to keep it in the fraction form. So again, if you have a root someplace, a root in the numerator or in the denominator, like how we first started with this problem, try multiplying by the conjugate. Usually that gets, multiplying by the conjugate always gets rid of the root. That's what you want. You want to get rid of that root. So again, there's just another trick that you can use. Now, like I said before, don't get into this mindset of, oh, it has to work this specific way all the time, because no, it just doesn't work like that. There's millions of tricks, and it's just you got to play with it, right? How do you know you're on the right track? It's because ultimately stuff is slowly canceling. Like when we first multiplied by the conjugate, we got all this stuff down here, and yeah, it looked bad, but what happened? Things started to cancel, right? And eventually we were able to get rid of that issue that was giving us a 0 in the denominator. That's what you're ultimately trying to do. All right, so those are limits with, rationals and polynomials, but another one that's kind of tricky is this right here. So now we have the limit as x approaches 0 of the absolute value of x. This one's tricky, right? Because what is absolute value? Remember, absolute value is a weird function, right? It was like a v. Y'all remember that? Maybe from 130. This is the absolute value of x right here. Now, in order to examine the limits with absolute values, we have to actually break it apart into two different functions, or like a piecewise function. Because what is this really right here? This is two different lines, right? Two different straight lines. You have a straight line right here and another straight line right here. They are absolute values will be linear like this. So what are we going to do? Well, we can break it apart. The absolute value of x is, well, let's look at how this thing is behaving. Well, right here, this is just a plain old straight line. This is just x right here. But how does it behave, or when does it begin to behave as just x? Well, it does that if x is greater than or equal to 0. Where did I pull this x from right here? Well, the trick to working these absolute values is the one where it's always greater than or equal to something, you just drop the bars right here. You don't change the signs, okay, of what's going on the inside. I'm going to do a couple of these right here. Now, what about the other side, right? Because it's a piecewise function. This is a negative line. It's just negative x. So the trick to doing the other piece is you slap a negative in front of whatever's inside of this right here. The parentheses are important because sometimes you will have more than one term inside, and that will affect your answer. Now, where does it behave like negative x? It's if x is less than 0. So the way these absolute values work when you're examining a limit regarding them is that you have to break it apart into two pieces, okay? One piece will always be greater than or equal to what makes the inside 0. And that first piece, again, you just drop the absolute values. And then the second piece is if you were to apply a negative to what's inside the absolute value, and it's always less than whatever makes this 0 right here, or whatever it is that you're analyzing. And then we're going to work the more that are way more complicated than this right here. But now we're not finished, right? Because remember we were asking, what is the limit as x approaches 0 of absolute value of x? So what do we need to do? Remember, in order for a limit to exist, it has to approach the same value from the left side and the right side, right? So what we need to examine is, does the limit as x approaches 0 from the left-hand side of absolute value of x equal the limit as x approaches 0 from the right side of absolute value of x? Are those going to be equal, right? If they are equal, then we could say, oh yeah, the limit does exist. I mean, you can look at the graph and say, yeah, they're both approaching 0, right? We could see, oh yeah, as I come from the left towards x equals 0, y is going to 0. As I come from the right, y is also going to 0. So it's 0. But this is how it's done right here. This is how you show it algebraically, because sometimes it's not going to be so obvious. So how do we do that, right? Well, remember, 0 from the left-hand side, which function are we going to use? The green one or the red one? You're going to use the red because that says x is less than 0. That's the stuff to the left, coming from the left of 0. So this is the limit as x approaches 0 from the left of negative x. That's what we're going to be looking at. And then the right one, or to the right of 0, correct? We're going to be using the positive function. So the limit as x approaches 0 from the right of just x. So again, I'm just using what we obtained from the piecewise function to work this out. So let's simplify, right? If right here I can throw this 0 in because there's no issues, there's no restrictions. So we wind up with 0 equals same thing on the right hand side. We can plug 0 into this function because there's no restrictions, there's no issues. So we get 0 equals 0. So is this a true statement? Yeah, it's true, right? Remember, for the limit to exist, the limit on the left side must equal the limit from the right side, which in this case it does. So ultimately, like your final answer is the limit as x approaches 0 of the absolute value of x is equal to 0 right here. Now, if we got two different values, correct? That would say, that would tell us, oh, this does not exist right here. So yeah, did you have to sit here and break it apart into two pieces like this, a piecewise? I mean, no, because if you recognize what the graph is, but that's not always going to work, right? Because sometimes you'll get something where you're just like, I don't know what the graph looks like. And you could make up a t-table, but you're going to sit there all day trying to figure out what exactly it's doing. So it is very important to realize you have to break it apart into a piecewise function. So let's try another one that's more difficult. All right, what if we take something like this, right? We're still dealing with the limit as x approaches 0 of the absolute value of x, but I throw an x in the denominator. See, now this, the graph of it, who knows what it looks like? I don't know what it looks like. Do I need it? No. We can still figure out what the limit is, though. We're going to break it apart into two smaller functions. Now, what do you do, though, with this? The only part that you need to break apart into two smaller functions is the absolute value case. This right here. Just break this apart. You know what the graph of this looks like. The absolute value part will always be basic. We already saw it, right? It was a v right here. We know that already. This is the absolute value of x. And we saw, oh, this is x right here when x is greater than or equal to 0. This is negative x when x is less than 0. That doesn't change right there. Yes, it can shift around. We're going to check one out like that after this problem. So how does this look if we were to write it out as a two piecewise functions? Because we have more stuff floating around, right? We have this extra divided by x right here. So the easiest one to start with is the greater than or equal to 0. Remember, always greater than or equal to this value. Remember, where did this value come from? Because we're pretty much looking at this right here. Remember, the greater than or equal to is just the initial function, right? And what do we do with the first case? We just drop the bars. So it's this right here. That's it. That's what happens if I were to drop the bars, right? And then for the left-hand case, or the case less than, that's the one where you apply the negative to the outside of your absolute value. Notice though, I didn't change the sign of this x, okay? The only thing that negative is being applied to is whatever is or was inside of the absolute value. All right, don't sit there and put a negative up top and a negative on the bottom, because this x was not inside the absolute value. Again, that negative only applies to what was inside the absolute value. So remember, in order for that limit to exist, we want to figure out or see, does the limit as x approaches 0 from the left equal the limit as x approaches 0 from the right? Like, that's what we want to see if it's true or not, right? Is that going to be true or false right here? So remember, since we're approaching 0 from the left, we're going to be using this particular function right here. So we have the limit as x approaches 0 from the left of negative x over x. That's this one right here. Does that equal the limit as x approaches 0 from the right of positive x over x? That's this one, right? I'll put this in red. That way you can match it up. So we have two smaller limits that we're looking at. And remember, how did we start this section? We said, oh, well, if we can plug these numbers in and we don't have an issue, we're good to go. But if we plug 0 into either of them, we do have an issue, right? You get 0 in the denominators, which is an issue. But what do? We try to manipulate the expression algebraically to get rid of that problem. And we can, right? Right here, because what is negative x over x reduced to? That becomes negative 1, right? These cancel out. Negative 1 over, or negative over positive is a negative. You're not left with nothing, you're left with negative 1. What about the right-hand side? What's x divided by x simplified to? 1, like that. So does negative 1 equal 1? Obviously, no, this is false. So the limit does not exist. Because again, we got two different values, right? One value from the left, another from the right side. They are not equal. So if they're not equal, the limit does not exist. If they're the same values, right, like both negative ones, then we'd say, oh, the limit's negative 1. And yes, if you had a graphing calculator, you could punch it in, right? You would see that probably if I just drew a rough sketch of this thing, it's probably doing something like this right here. This would be a solid circle. This would be an open circle right here. This is negative 1, positive 1, like this. You would see, oh, well, as I approach 0, x equals 0 from the left and the right, they're not homing in on the same values. This is what's happening right here. But again, don't try to figure out, oh, what the graph is. Break it apart into two functions all the time, because that will always be a lot easier. All right, so let's try another one where we don't necessarily have just a regular x, or just an x, you know, inside the absolute value. So now we have the limit as x approaches 5 of 3x plus the absolute value of x minus 5. A little more complicated, right? Because we have this 3x additionally, and we have something inside with the absolute value. It's no longer just an x. So what do? We're still going to do the same thing that we did for the last two problems. We're going to break it apart into two smaller functions as a piecewise. So how do we do that? It's still the same case, okay? So if you want kind of like a trick or whatever, if I have the absolute value of stuff, right? Stuff could be anything. X minus 5, 9x squared minus 2x plus 8. It doesn't matter. You don't care what stuff is. It could be your name, absolute value of your name. How would you break it apart into a piecewise function? You're going to have stuff like this. And I'll put it right here. You're going to have the stuff. That's going to be the first one if x is greater than or equal to a. This is pretty much like the shortcut right here. And then the next one's going to be negative, and then in parentheses stuff if x is less than a. That pretty much takes all the guesswork out of what you need to do. But again, stuff could be anything. Like stuff in this case is just x minus 5. If we follow this little shortcut thing that I worked out right here, we're not going to have any issues. So let's try that out, right? Now you can have additional stuff floating outside of it, right? Like this 3x, for example. So if I break this apart, okay, this is going to be equal to, as a piecewise function, we're going to have, let's try it out. I'm going to have 3x plus, and remember, what was the stuff right here? Did I change anything on the inside? No. This is going to be x minus 5 if x, I'm just going to erase this little chunk. if x is greater than or equal to 5. So remember, where am I getting all this from? Where did the 5 come from? That's the a. What's the a? The 5. That does not change. The stuff right here was this. And then if you have, again, anything additionally floating outside of the absolute value, make sure you drop that down. That never changes. The stuff outside the absolute value, the signs of it, that's never going to change. It's only the stuff on the inside, okay? Now let's do the second one. So remember the next one from this little formula that I had or whatever, again, the only thing that's going to change is you're going to have a negative in front of the absolute value or the stuff. We still have the 3x, but now I have a minus sign instead. And what was the stuff? The stuff is x minus 5. If x is less than a. Well, again, what was a in this case? 5, like that. Really important, you always want to keep the parentheses around whatever was inside that absolute value. In the last two problems, it didn't make a difference because we only had that singular x. But right here, it is going to make a difference, right? Because what are you going to have to do? Distribute this negative sign into both of these right here. So let's see what happens, right? Let's see what happens if we analyze this limit right here. So remember, this is 5. This top one would be us approaching 5 from the right. This bottom one would be us approaching 5 from the left. So what we're asking is, does the limit as x approach 5 from the left of f of x equal the limit as x approaches 5 from the right of f of x? Oops, I don't need this. And that's the question mark right there, right? It's either gonna be a true statement, 5 from the left. It's either gonna be a true statement or a false statement. So let's see what happens, right? So if I'm approaching 5 from the left, which one of these do I need to use, the top one or the bottom one? I have to use the bottom one because that says x less than 5. This would be 5 from the left. So we're going to have the limit as x approaches 5 from the left of 3x minus x minus 5. And we're trying to see, does that equal the limit as x approaches 5 from the right? But remember, because we're approaching 5 from the right, we're not going to use this bottom function. We need to use this upper one right here, right? Because that's for any value bigger than 5, this one. And again, we're just trying to see, is this going to be true? That's why I put the question mark right there. So where do we go from this point? We plug the 5s in basically, right? To see what happens. So we have 3 times 5. 3 times 5 minus 5 minus 5. And we're just trying to see, is that, question mark, will that be equal to 3 times 5 plus 5 minus 5? So are they going to be true, right? Are we going to get the same numbers on both the left side and the right side? Well, in this case right here, they both have 5 minus 5, right? So that becomes 0, 0. And then we wind up with 3 times 5. Well, that's 15 equals 15. So yeah, look, we got the same value as we approached 5 from both the left side and the right side of this particular absolute value expression. So the limit does exist, right? It is 15. That would be your final answer right there. So remember, the trick to doing these is that little stuff trick, right? And it doesn't matter what you have in there. So we'll try one more absolute value. All right, so this one looks kind of nastier, right? Because we have now a rational absolute value expression. And to make it kind of worse, it's not that bad though, is that the absolute value is in the denominator. So what do? We're still gonna do the same thing that we did in the last problem, okay? So first of all, we definitely have an issue, right? Like if I plug 2 into here, we get 0 over 0, which is undefined. Not because the top is 0, it's because the bottom is 0, and anything divided by 0 is 0. So that's one thing. Another thing is that we have the absolute value, right? So we're gonna have to break it apart into two functions. But we can use that little stuff trick that I wrote, a little while ago. So remember, if you're looking back on your notes, the first one, I don't have the space. If we were to break this apart into two smaller functions, remember, the first one from that formula was what? It was just stuff, right? It was the stuff if x is greater than or equal to a. So let's do that first. We know it's greater than or equal to 2, correct? And the bottom one was if x is less than a or less than 2. So we got that. Now remember, for the very first one, it was stuff, right? So basically, what do we do? Don't forget to add the bars right here. What do we do for the very first one? You just drop the bars, but nothing changes basically. So we have 3x minus 6 over x minus 2. That's following that little formula thing that we wrote down. Stuff, you basically drop the bars for the first case and keep everything the same. Do nothing else. Now for the second one though, what did we do? We multiplied a negative into that stuff and kept everything else outside of it the same. So up top we still had 3x minus 6 because there's no absolute value associated with it, or it wasn't inside absolute value. But on the bottom though, we need to multiply a negative, right? That's what we did with that little formula. We said negative stuff like this. But notice again, the only thing that changes with these absolute values when you do these piecewise functions is the absolute value component. Everything else outside of that does not change. We never changed anything from the 3x minus 6's, right? We never changed the signs because those were not inside absolute value. We only changed basically the bottom one, right? Because that's when you have the less than version, it's negative stuff. Don't forget the parentheses though, right? All right, so what does this look like, right? So what are we doing? We're going to test the limits to see if they both equal the same thing from the left side and the right side. So we have the limit, or being asked, does the limit as x approaches 2 from the left of 3x minus 6 over negative x minus 2, does that equal the limit as x approaches 2 from the right of, remember we're using the top function, right? Don't forget, when y'all are writing this out, the left-hand version, you're going to be using the less than from the piecewise function. Approaching that value from the right side, you're going to be using the x greater than or equal to version. So let's see, is this going to be a true statement, right? So remember, at this point, you'd say, hey, can I throw this number in? Can I throw these numbers into here? If I don't have any issues, great, right? Issues meaning 0 on the bottom or some kind of restriction. Well, guess what? We have a problem. Because what if I plug 2 into here? We get 0 on the bottom. If I plug 2 into here, I get 0 on the bottom. So we have to somehow get rid of that algebraically. Use legal algebra. I say legal because people just make up stuff. They make up magic math. Can't do that, right? It's got to be legal. So what can we do, right? I mean, you could try to multiply this out, but that would probably make it look messier. And if you remember the first thing I said, when you're trying to figure out what can you do, is just ask yourself, can I factor something? Is there a GCF? Something, right? And there's a GCF, right? Look, both of them have the same GCF. What's nice about these problems is whatever you do to one algebraically, you're probably going to do the same thing algebraically to the next one. So look, we can factor out a 3 up top, right? If I do that, I have 3 times x minus 2 over negative x minus 2 equal the question mark. Same thing right here. We have 3 times, and that becomes x minus 2 over x minus 2. So if I plug the 2 in still, like 2 from the left, 2 from the right, we still get 0 in the bottom. We get 0 over 0, which is bad. But we can cancel, right? Look at that. We can knock out these x minus 2's. Now, remember because these x minus 2's are canceling, it's not that we're left with nothing, right? Don't say, oh, I have 3 over nothing. No, nothing means 0. You have 3 over a negative 1, right? This is 3 over negative 1. And this is equal to 3 over positive 1, right? Because that's what's left over. But then, of course, you keep simplifying, right? Does negative 3 equal positive 3? No, this is false, obviously. So the limit does not exist. As you can see, it doesn't matter where the absolute value is, right? We just do that. Go back to that little stuff formula that we wrote out. Your first version is always going to have stuff, just dropping the absolute value bar, changing no signs, keep everything else in the entire problem the same, right? Like what we did right here. We just drop the absolute value if x is greater than or equal to whatever that limit is that you were examining. In our case, it was 2. And the next one is the negative of that stuff, right? You throw it in parentheses, but again, you keep everything else the same if x is less than that particular a value or whatever the limit is you're examining. Then you're going to sit out there and you want to see if they match up, right? Like if you were to dump that number into the left piece, will be equal to the number on the right piece, meaning you approach that x value from the right side. And of course, sometimes they won't match, right? If they don't match, then it does not exist. If they do match, then the answer is whatever that limit is. Is there a question? I see like a hand up thing. Shanera?
Yes.
Yeah.
How do we go from 3x minus 6 to 3x minus 2 at the top in the
Oh,
numerator?
yeah, this, we're factoring out a GCF, right? Like, what do they both share in common? You see, I can pull out a 3, right? Remember, factoring out means dividing out. So that I found basically a common multiple right there.
Oh, I got you.
Yeah. Remember, you can always check too, like, did I do it? How can I see if I did this correctly? If I distribute back 3 times x is 3x, and 3 times negative 2 gets you back to negative 6. So you can always check that out right there as well. But that's what
Got
you
you.
want for. Yeah. Always do they, that's the very first thing y'all should always do, like with the factoring. Do this before the factoring. Ask yourself, is there a GCF? Then if there isn't, can I factor it? And then something else and so on. But yeah. All right. So one more problem with this, and then we will get out of this section. We'll check out a piecewise function. All right, so there is no absolute value right here. This is just 2 random functions. Okay, this specification right here, they're just making that up for x greater than or equal to negative 3. for x greater than -3, they just decide that random value. Usually it'll be associated with whatever that limit is right there. But no absolute value right here. How do we work this out? Well, it's pretty much like the last step that we were doing with the absolute value functions, where we had to compare the limits, right? Because remember, a limit exists if the limit from the left side equals the limit from the right side. So they kind of did the hard part, right? They already broke it up for us into these two equations right here. So what are we going to do? We're just going to ask ourselves, does the limit as x approach -3 from the left side of f of x equal the limit as x approaches -3 from the right of f of x? That's all we want to see. I think the absolute value ones are more difficult because you have to get it to this point right here. And then you got to go out there and calculate. Right now, we just need to calculate, right? Because it already did the dirty part for us, the dirty work. So the only thing you need to watch out for when you're doing these is make sure you plug in this value into the correct equations, right? Like if you notice it says -3 from the left, which one are we use, the top one or the bottom one? Well, you'd have to use the bottom one, right? Because of the it says, oh, use this one when x is less than or equal to -3. That's what we got right here. So we're gonna plug -3 in. I remember, watch the signs, right? -3, you got to square that whole quantity right here. Be very careful with the negative. The negative also has to go on the inside, right? Because it's the x value that we're looking at. And then equals. Is that going to equal? Well, now let's look at the limit as x approaches -3 from the right-hand side. We have to use the bottom equation in this instance because this one says use me, 2x plus 3, for any x that's bigger than -3. So are we going to get the same values, right? Let's find out. This is 9 minus 6 equals -6 plus 3. Okay, so we get 3 equals -3. Well, what does that mean? So that tells us that the limit does not exist. So if we got the same values, correct, like 3 equals 3 or -3 equals -3, then the limit would exist and it would be that number. But because they're not the same, the limit does not exist right there. Remember, on the web assignment, you put D and E for those particular expressions. All right, let us move on to 2.5. Two 2.5 still deals with limits. It's just now we're dealing with continuity. There we go. Continuity. Mainly we're talking about where or when is a function continuous. And usually they always ask that at specific points, not across lines, but mainly around points. Points that could give us problems, right, or issues. So there's 3 things that we need to remember in order for a function to be continuous at a certain point. So a function is continuous at x equals a if, and we have three guidelines or 3 criteria that must be met. The first one is if f of a is defined. The second one is if the limit as x approaches a of f of x exists. And then the third is kind of like you're wrapping up the first two together. If the limit as x approaches a of f of x is equal to f of a. So what does all this mean, right? What are examples? What I'm going to show you is examples where each of these three conditions fails individually because it's easier to see where it doesn't work instead of where it does work. All right, so I'm going to give you an example of what something is or where something is not defined. So let's say we have a graph. Here's that x value a, and you have a nice open circle right here. Remember, if you have an open circle, that means not included. So it's not included, it is not defined. And if you remember from the last class on Monday, when we were looking at those graphs, if you had an open circle, I said, oh, the limit could exist, right? Like the limit does exist right here. Because if I approach a from the left side and the right side, they're both homing in on that same value right here. But if I asked you, remember we had problems like, oh, what is f of a? Meaning if you could get land right on top of a, what would the y value be? But in this case, you can't land right on top of y, right? Remember I kept saying you fall through the hole or you fall in a hole, whatever. The only way that this would be defined is if it was a solid circle, which it isn't. So in this case right here, f of a is not defined. Since it's an open circle. Anywhere else on this problem, like let's just say if I said this is B right here, like this is the point B. B, it would be continuous at B, right? Because you have a solid circle, the limit exists, correct? Like as I approach B from the left and the right, it's going in the same direction. And then the third condition would be satisfied as well. They would both of these are equal to the same number. But we'll get into that more in a little while. Right now, I'm just showing you conditions where it fails. That's an example of the first case not working. An example of the second case not working, meaning that the limit of f of x wouldn't exist. Let's just say this is a again, correct? Here's x equals a. Right here, we could say f of a is defined. Why? Because you have a solid circle right there. You see, it's kind of like, oh, we could say it's a third of the way continuous, but with continuity, it's either all or nothing. So you can't say, oh, it fits the first rule and the third, but not the second or whatever. It's got to satisfy all three rules or conditions in order for it to be continuous at that point. But at this case right here, the limit as x approaches a does not exist. Why not? Because we'll look at it. Remember, in order for a limit to exist, what must be true? That as you approach that particular value a from the left side and the right side, they home in on the same y value. Do they right here though? No, because as I approach a from the left, we're down here with y. But as I approach a from the right, we're up here with the y value. So no, they don't match. That's why the limit does not exist in this case. And therefore, it is not continuous at a. And if we do the third, an example of the third case, So we're looking at failures, right? Remember the third case said, oh, the limit as x approaches a of f of x is equal to f of a. But right here, that's not true, right? So look. So I'm putting does not equal f of a. Let's look at that. So there's a limit, right? The limit does exist because as I approach a from the left and the right, they both home into this same y value. But remember the third condition, but the thing is, as far as f of a being defined, where is it defined at? It's defined up here. You see that? In order for this to be continuous at a, where will this solid circle have to be? It have to be right inside of that open circle right there. So you got to pay attention to this one right here. This is the one that throws off people a lot because they say, yeah, I was able to find the limit. But we're not talking about limits, right? We're talking about continuity, or is it continuous at this particular a value or x value? And I kind of mentioned it also too from the last class when I was drawing a sketch, right? If you can draw a sketch successfully without lifting your hand off the paper, then maybe you do have something that's continuous. Well, I don't want to say maybe because I know you can draw this one, but it's not continuous. But in this case right here, you can't, right? Because you'd have to lift your hand off the paper or tablet, whatever, to get to this dot right here. But it's better to remember these three rules, right? This one right here, again, is the trick one because a lot of people say, yeah, the limit exists, so therefore it's continuous. But it's not continuous though because f of a and this limit are two different things. Why? Because f of a is actually this upper value right here. This circle would have to be down here in order for it to be continuous. So saying something has a limit is part of saying something is continuous, right? That's what you have to remember. So these are the three conditions of it failing. All right, so why is the function discontinuous at a? So when they ask you this, like it does pop up in the homework, it's failing at least one of those three conditions, right? It's like on the homework, you'll be able to check more than one condition, okay? So let's go over that. Like, why is this thing discontinuous at A? So remember the three rules, right? F of x has to exist right here. That's the first one. Or f of a is defined. That has to be one thing. F of x, the limit has to exist. And then both of those two values have to be the same. Well, let's start with it. Is f of a, is f of -2 defined? You just work your way down the list, right? All three. And say, and then see which ones fail. So is f of -2 defined? The answer is no. Why? Because what is f of -2? That's 1 over -2 plus 2, which is 1 over 0. But that's undefined. Right? Because anything divided by 0 is undefined. So that's one of them right there. Does the limit, say this is the first one. The second one, does the limit as x approaches -2 of 1 over x plus 2 exist? Well, remember, this is the one where we have to look at the t-table, right? You would make a t-table and choose values smaller than -2, bigger than -2, and you would see where they're going. There's no algebra tricks that we can do like we did with those limit problems from a 2.4, unfortunately, or I'm sorry, 2.3. So you'd make a t-table. I'll leave that up to you guys. I'm just going to draw the sketch of it really quick. So you're pretty much going to have a vertical asymptote at x equals -2. And your graph is going to do something like this right here. So as you can see, the limit doesn't exist. Why? It's not, remember, we can't have infinite limits, right? You may be saying, oh, but it's going down to -infinity and positive infinity. Those are limits. It's true, yes, those are infinite limits. Remember, in order for a limit to exist, what has to be true? It has to approach the same y value from both sides. So are these approaching, or as x gets closer to -2, is it approaching the same y value from both sides? No. This side's approaching -infinity. Coming from the right, as you get closer to -2, it's approaching positive infinity. So the limit here does not exist. So it's failing the second condition. So now, what about the third condition? Does it pass the third condition? Remember, the third condition was asking, does the limit as x approaches -2 of f of x equal f of a, or f of -2 in this case? That was the third criteria, right? Like, do those two values match? Or we just saw that they don't, right? We just took the limit as x approaches -2. That's a D and E. We got does not exist. And was that equal to f of -2? No, no way. Once once one of these fails, the third condition automatically fails. You don't even have to worry about that. But if you want, you can go through the checklist like this. Just start with the first 1, 2, and 3 like that. If the first one fails, though, it's game over. I mean, you know that the other two aren't definitely going to work. You know the third one definitely won't work because these values aren't going to match right there. And again, what do we do right here? Well, I know I drew the graph, but going back to the old way, you can make a t-table, right? Like you could choose -1.9, -1.99, for example, like this. Remember we did this last class. We chose values slightly. Let me just erase. Like for that t-table, you would choose values slightly smaller than 2 and values slightly bigger than 2, right? But what you would see is, according to this graph, right? Like the closer I get to -2, this is undefined. The closer I get to -2, the smaller my x values would get, right? Like if I plugged it in, I'll do it really quick. And it's kind of hard to see, like you get 0.2564 with a bunch of decimals. Then when x is 1.99, you get 0.2506. So yeah, it's not this drastic drop like, oh, they're getting smaller super fast, like this was -10 and this was -50 million, right? But this one is smaller than this one right there. So that does indicate that it's going towards negative infinity. Likewise, if we did the same thing for this other one, or for the right-hand side, we actually get 0.2439 and 0.24, yeah, 937. So as you can see, as we get closer to +2, what's happening right here? Again, it's not a big jump, unfortunately, right? But this is slightly bigger than this one. This is 0.249. This is 0.243. So as we get closer to 2, it's actually increasing, right? So that indicates, oh, it's going to positive infinity from the right. All right. Now, what if we have this function? So we're still doing the same thing, okay? So we have a piecewise function. We're trying to see what we're being asked. Remember, why is this thing discontinuous? Why is this thing discontinuous right here? So we know there's some kind of problem, right? We just have to state which one of the three, could be more than one, is it failing? So let's start with the conditions, right? Like, oh, the first one was, is f of 0 defined? So is f of 0 defined? What does that mean? Can we plug 0 into here and will some kind of y value that exists pop out? But yeah, I can plug 0 into here. Why? Because this one says, look, it says for x squared, we can use that one if x is greater than or equal to 0. So yes, f of 0 equals 0 squared, which is 0. So that checks out. You're not going to plug that 0 for the first condition. You're not going to plug it into e to the x. Why? Because this says if x is less than 0. This first condition is saying is f of that specific value defined, and we can jam it into this bottom one because this one says yes, I can include 0 right here. So we got a number that exists, that works out. So that's not a problem. What about the second one? The second one says, what about the limit as x approaches 0 of f of x? Does that exist? Well, remember, when does the limit exist? It exists if the limit as you approach x from the left side is equal to the limit as you approach x from the right side, correct? If their y values are the same. So we have a piecewise function right here, right? So we need to figure out again, does the limit as x approach 0 from the left of f of x equal the limit as x approaches 0 from the right of f of x? Question mark, just like that. So we have two different functions, right? You got to pay attention to that right there. 0 from the left. Which one are we going to use? The top one or the bottom one, and why? Well, we're going to, for approaching 0 from the left, we're going to use the top one. Why? Because look at the domain restriction. It says for any x smaller than 0. Well, if I'm coming from the left of 0, that's all the x values smaller than 0, correct? So this is going to be e to the 0 power right here. That's this one. Equals. So for the right-hand side, limit as x approaches 0 from the right, that means we got to use the second one because the second one, its domain restriction is saying we use x squared if x is bigger than or equal to 0. Coming from the right of 0 is everything bigger than 0. So we're going to have 0 squared. So make sure y'all pay attention to the domain restrictions. Those are important because that's going to tell you which function you plug in your a in. So now we have e to the 0. And then we have 0 squared. Are those the same? There's another little arithmetic thing that people get confused with or make a mistake on. E to the 0, what is that? It's not 0. Remember, anything that exists raised to the 0th power is automatically 1. Remember, what is E? E is a business number. E is just equal to about 2.71, right? That's like a number they use in finance. Your calculator, if you have a TI-30, you press E and enter, it's going to spit out 2.71, blah, 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 like that. The basic graph of it looks something like this right here, if you forgot that too. And this is it always passes through, that's 0, 1. This is e to the x right here. And that makes sense, right? Because if I plug 0 in, I get 1 for y. So we get 1 equals, what's 0 squared? Well, that definitely is 0. Does 1 equal 0? No. So the limit of f of x does not exist right here. You see, it's failing the second condition right here. Would it fail the third condition? Well, yeah, because again, if it fails either 1 or 2, it's definitely going to fail the third condition. What did the third condition state? The third condition was basically saying, does the limit of f of x equal as x, well, in this case here, as x approaches, what were we looking at? We're looking at 0. Does the limit as x approaches 0 of f of x equal f of 0 in this case, right? Because that's what had to be met for the third condition. Well, the answer is no, because we found out what the limit was as x approaches 0, right? The limit as x approaches 0, when we did that, what do we wind up with right there? We got a DNE, right? We got a DNE. That means game over no matter what, equals f of 0. What was f of 0? Well, remember, we were able to plug 0 into the x squared, right? Because this domain restriction said x is greater than or equal to 0. So we got a DNE equals 0. This is false, obviously, right here. So it's failing the third condition as well. Like I said, if it fails 1 or 2, the third one's automatically gone, because in order for the third one to even possibly work, 1 and 2 both have to be continuous or check out with their respective criteria right there. But you see how we're doing it, right? We're just taking steps 1, 2, 3, and just seeing which ones work and don't work. All right, continuing with this. We can say a function is continuous from the right at a if the limit as x approaches a from the right of f of x equals f of a. Same thing can be said for approaching it from the left side. All right, so we're gonna do a nice little monster problem right here. It's gonna have 3 parts. So it's gonna put all this together. So from the graph, states the numbers at which f is discontinuous and explain why. So that was like this is A right here, sorry. A. And then B is for each number stated, in part A, determine if f is continuous from the left, right, or nowhere. And then part C is to label the intervals of continuity. All right, so now I'm going to go out here and I'm going to erase all this. So I got to draw this big old picture. I wish I had a bigger board. All right, so with discontinuity, where can it happen at? Or you may be thinking, where do I start with all this discontinuity mumbo jumbo? Well, the only spots where you can have discontinuities where you have open or closed circles. So that tells you right there, well, we're probably going to have something some issues at -4, -2, 2, and 4, right? Because we see circles around those x values. That tells you right there that's what you're dealing with. So you always want to start from the smallest, to the biggest. So remember we were being asked about for part A, state the numbers at which f is discontinuous and explain why. So the first one is that x equals -4. Now remember, we have to explain why. That's very important. That's the most important part. It's not the numbers, it's why. So remember, there were those three conditions, right, that we had to meet. The first one was that f of a had to be defined. The second one is that the limit exists. And the third one is that both the answers from 1 and 2, conditions 1 and 2, were the same. So remember, to start with the very first one, is f of a defined? Remember, defined means you have some kind of solid circle at that x value. Do we have a solid circle right here? No. So f of -4 is not defined. And remember, the reason why it's not defined is there's no solid circle. The limit does exist though, correct? Why does the limit exist right here? Because if I approach -4 from the left and the right, they both home in on the same y value. But remember, we're not being asked about what the limit is, we're being asked about continuity. The next x value where you have an issue, again, look at the circles, right? Open and close circles, is that x equals -2. Why is it discontinuous right here? So remember, condition 1 says, oh, f of a has to be defined, or f of -2 has to be defined. Is this defined right here? Yes, it is defined. Why? Because you have a solid circle, right? So f of -2 is defined. And you can say, oh, because there's a solid circle. That's okay. But does the limit exist right here? No. But the limit does not exist. Why does the limit not exist? Because remember, in order for a limit to happen, or I'm sorry, not happen, be true or exist, is that you have to be able to approach that particular x value from both the left and the right hand side, and they must approach the same y value. Is that happening right here? No, because as I approach -2 from the left, our y value is up here. As I approach it from the right, towards -2, it's down here. They're not equal. So the limit does not exist. That's why it is not continuous at -2. Now, if we go to x equals 2, now we're over here. This is pretty much the same situation as this one, right? It is defined because we have a solid circle, but does the limit exist? No, because as we approach 2 from the left, we're getting one y value that's different from if we were to approach 2 from the right, right? We're getting two different y values right here. So the limit does not exist. Remember being asked why does it fail, right? Why is it not continuous right here? And then on the WebAssign, they'll have like check boxes that say, oh, it's always going to have these options listed, or a little drop down box menu where you select the reasoning why. And this is why at x equals 2 is because the limit does not exist. And then if we go to the fourth one, we get x equals +4, right? That's the other issue, because you have a solid circle up here. On the left side as well, it's doing something weird. It's actually going to -infinity, right? Like if I drew arrowhead, that means it's going to -infinity. So again, start with the three conditions that must be met. The first condition is f of 4 in this case defined? Well, yeah, you got the solid circle, so you're okay. But the second condition is, does the limit exist right here? No. Remember, when does the limit exist? It's because when you can approach that particular x value from the left side and the right side, they are approaching the same y values. That's not the case right here, right? The limit as you approach 4 from the left, coming from this way, where is it going? Your graph's going down to -infinity. The limit as we approach 4 from the right, it's definitely not going to -infinity. It's going to some positive y value. Do we care what that y value is? No, because what matters is that the y values are not the same. So the limit does not exist. That's why at 4 it is discontinuous. Now for part B, so I'll still keep the graphic there. Part B was asking for each number stated in the part A, determine if f is continuous from the right, the left, or neither. Okay. So continuous, right? Remember, continuous again had those three conditions, right? So at x equals -4, why is it going to be continuous from the left side or the right side? No. What determines continuity, okay, or whether something's continuous is the open or closed circles. Pay attention to that right there. The gist of it is that what's wrong with marker? Come on. Open. Let me add this right here. Open circles mean not continuous from a particular direction. So if you had a solid circle, it would mean that yes, it is continuous from that particular direction. Now at -4, you may be asking, well, what direction from is it continuous from the left or the right, or is it not continuous? Because we see an open circle, correct? So it's got to be not continuous from some direction, the left side or the right side. Well, it's actually both in this instance, okay? This one right here at x equals -2, we can say that x is continuous from the left side because if you're approaching this graph from the left, you have a solid circle right there. But would it be continuous approaching -2 from the right? No, because of the open circle right there. So that's what I mean from a particular direction. So with x equals -4, it's neither continuous from the left or right. And why is that? Because we had an open circle right here. If you have a line with an open circle just like this all the time and no jumps like this, it's not going to be continuous from either side. And again, it's the open and the closed circles that determine that right there. Now for now at x equals -2, again, it's solid and closed. Solid circles means that it's continuous from that direction. Open means it's not. So if we approach -2 from the right, y'all see what are we happening or what's happening? We're running into a solid circle. That means we are continuous. Man, these markers just love dying. So or just talking about x equals -2, we're continuous from the left. And again, it's because solid circle, right? You can make a little note, solid circle. But we are discontinuous from the right. And that's because you have an open circle. Moving on to positive 2, again, open, closed circles. You have combinations, but as we approach 2 from the left, you're running into an open circle. That means discontinuous right there. So discontinuous from the left. And again, it's because you have that open circle, right? We have the open circle right there from the left. But it's continuous from the right. So as we walk towards positive 2, x equals positive 2 from the right, we're running into a solid circle. Remember, this problem was asking where is it discontinuous from specifically, but I'm just putting in the continuous parts. That way you guys have a reference. So, but make sure y'all read the directions because I believe on WebAssign it's just asking for where's the discontinuous at. So don't sit there and say where's the continuous part. It's not asking for it. That's right. It's not asking for it. It's specifically asking for the discontinuous part. But it's important to understand where all the stuff's happening, right? The discontinuous and the continuous. Now, for the last one at x equals 4, right here, right? Well, we have a solid circle up here, right? So we know that it's continuous from the right. But then it's, as we approach 4 from the left, even though there is no circle, it's implied that it's going down forever. If it's going down towards negative infinity. Remember, infinity and negative infinity, they're not finite numbers. Infinity just means a really big number, or negative infinity means a really small, a really super small number. We don't know how big it is. If we knew how big it was, then it wouldn't be infinity, right? Like if it was 50 quadrillion or something, even though that's super huge, it's still a finite number. So this is heading as we approach 4 from the left, even though there's no open circle, if something's going up forever to positive infinity or down forever to negative infinity, that denotes that it's an open circle because, again, we don't know how big or how small infinity or negative infinity are. Those are just, that just means conceptually a super large or a super small number. So it is continuous from the right, again, because we have a solid circle, and then it's discontinuous from the left. Because we're basically going to negative infinity. To make a note right there, if you're going to infinity or negative infinity, that means it's discontinuous when you approach that particular x value from that direction. All right, and then finally to part C. C just wanted the intervals of continuity, like where is this thing continuous? Now, this basically goes, when they ask you for the intervals of continuity, they're basically asking what's the domain of this. It just means for the domain of the function. So when, again, when they ask you for intervals of continuity, it's just a fancy way of saying what's the domain of the function. And for those of you who took 130, remember we did 130 50 million times, right? It's like every single section was always saying, oh, by the way, what's the domain? What's the domain? It was ridiculous. So it's the same thing right here. Intervals of continuity just mean what's the domain of this function right here. And remember, domain is just all the x values that our function exists at, correct? Like where is it going, right? Across the x values. The y values are irrelevant right here. It's just you're listing where's the smallest x value that you begin to sketch your curve from until what point. And you could have stops, right? Like what the main thing that determined whether you had stops was if you had circles, right? And of course, when we did this in interval notation, you had brackets and you had parentheses and all that good stuff, right? Like remember, if you had an open circle, that meant parentheses, or if you had a solid circle, that meant brackets, right? Like we had things like that right there. So yeah, and you could have combinations of them, but we're definitely gonna have them right here. So remember, when you have multiple intervals of continuity, you always start with the smallest x value. Remember, we're trying to figure out where's the smallest x value that we begin to sketch from. Like you imagine you're giving somebody directions, right? And you're like, I need you to draw this curve. And you gotta tell them, what's the smallest x value that we start at? Remember, arrows mean they're shooting off forever. So what's way off forever over here, to the left forever along the x-axis, is negative infinity. So that's where we start in this case. So we start sketching our curve, you know, la la la, from negative infinity all the way, and we have a circle. Remember, at circles, you got to stop because something's happening right there. So from negative infinity to negative 4, we have our first little amount of x that we're tracing. But now we have to enclose them with something, right? Parentheses or brackets, a combination of them. Infinities and negative infinities always get parentheses. You don't care what else is happening in the problem. Those always have parentheses. You will never be equal to those. You will never get to them because again, it's a conceptually large, super large number or a super small number. Now, what about the negative 4? What are you going to have around that? It's got to be parentheses. Why? Because you have an open circle. That means not included. WebAssign, be very careful, right? Don't just put all parentheses or all brackets. It definitely depends on, again, the circles, whether they're solid or open. That's that first gap, right? That's basically all this to here. Now we need to pick it up again. Where does it start back up? Again, at negative 4, right? Why is it? I know you're asking about how it's not included, but we still have to start super close. How are we going to denote that though? With a parenthesis around the negative 4. Remember, parenthesis why? Because it's an open circle right there. That just means not included. And we'll continue sketching this curve with respect to x until what x value? Negative 2. Notice how too when I separated the intervals, I just put a comma. That's how you'll do it on WebAssign. I know sometimes you'll see like a U. People have used union. That's definitely doable as well. But WebAssign does commas, so we're going to do commas. So from negative 4 to negative 2. But now, how are we going to enclose the negative 2? Well, this time you're going to use a bracket. Why? Because as you approach negative 2 from the left, which we're doing right here, solid circle, right? It was continuous from the left. And then where do we pick up again? Well, we have to now identify this chunk, right? This interval right here. What is that? That's negative 2 to 2. But how are we going to enclose those? Parentheses. Why? Because of the open circles. Then we have the next chunk. So it's kind of weird, right? We got this and all this right here shooting down. But this, remember, what's it doing? It's not, this line's not crossing on top of 4. You can almost kind of, if you want to, you can imagine there's like a, almost like a vertical asymptote right there, kind of. So that segment, right, is from 2 to 4. Now in this case though, the 2 is gonna have a bracket. Why? Because of the solid circle right here. It is continuous from the right. But the 4, is that going to have a bracket? No, because it's not continuous from the left side. It's going down, remember, towards negative infinity. That has parentheses. Now, what about the next segment, this chunk right here? Well, we know that starting at 4, And arrowhead means it's going what's way off forever to the right along the x-axis. Positive infinity. So it's going from 4 to infinity. What are we going to do? How are we going to enclose this? Well, bracket around the 4. Why bracket around the 4? Because you have a solid circle. And infinities, and remember, negative infinities always have parentheses right there. So if you notice, you can have mixtures of parentheses and brackets. Sometimes you could have two parentheses as well, just like what we had right here, right? It just depends on what your curve is. There's no rhyme or reason, no patterns or anything like that. It just depends on where the circles are. But the main thing to take away is when they ask for the interval on which a function is continuous, they're just asking for the domain, right? So open circles, you have parentheses around those values, right? Like around the -4. If you have a solid circle, depending on which direction you're approaching it from, you can have a bracket like what we did right here. Remember, this -2 with this piece right here does not have a bracket. Why? Because approaching -2 from the right, it was an open circle right there. Opens are always parentheses. Approaching from the right for x equals 2, it was a bracket. Why? Because we had a solid circle right there. Same thing with the 4 in this instance right here. So that wraps up this particular section. Now, something I want to remind y'all is that Respondus quiz, the one to get you familiar with the Respondus Lockdown browser, it is due on Friday. It is true that it's not worth anything at all. It's not worth the test grade, but you should take it anyway just to make sure that the software, the Respondus stuff, and the webcam and all that good stuff is working, because you don't want the first test to come up and all of a sudden something's not working because you never tried it out, right? So please take that thing, and that way you can get familiar with the Respondus if you haven't used it, and definitely most importantly to make sure that all that stuff is working, okay? You should be able to take the quiz. Some people have already done it. Again, it's not worth anything. It's just, I don't even think it has anything to do with math. It's just an info. It does. It's just very basic questions. It's just, again, to get you more familiar with that Respondus lockdown browser. But if you're having issues with it, then send me an email or something, or we can get on this Zoom thing, and we can do screen sharing. We can see what the issue is with that right there. Are there any questions with this right here? So this lecture will be posted. It does take a while because the video file, like from last time, is super huge. So if y'all are gonna check for it, it's not gonna be up in like 10 minutes, unfortunately. I would probably check for it tomorrow morning. I know definitely for sure it'll be uploaded by then because it's an automatic process. So now what I'm doing is I'm saving these videos into the Zoom iCloud. Okay, so when y'all click on the Zoom tab, there should be another little option that says videos right there. I know I posted the first one on YouTube under the, what was it, the pages tab, but now all these Zoom files should be coming in through the Zoom tab itself. They won't be posted under the files tab under YouTube. So we'll see how that works. If not, I'll just transition it back to YouTube. But right now, this one should be popping up under that the Zoom tab itself under the iCloud videos. But again, give us some time to upload because it's gonna, there's a 2-hour lecture that we just did. Okay. So any questions, comments, concerns? No hands up or anything. All right. If not, then that is it for the class, and I will see you guys on Monday. Again, if you have any questions, I'm here online with the Zoom office hours and all that stuff. If you have any questions, please hop on, okay? All right, bye-bye.